Hello everyone, good morning or afternoon or night if it's a late night study session. Today we are going to be talking about S and P hybridization and sigma and pi bonds. If you first heard about this concept and you were super confused, don't worry, so was I. When I first heard about it, I thought of the S&P 500 and I was wondering what kind of dividends these carbon atoms would be paying. So there you go, let's jump right in. Alrighty, let's dive right in here and see how to make this beautiful molecule called acetylene. The red dots represent carbon atoms and the green dots represent hydrogen atoms, and all the white stuff is all the orbitals and bonds. Start off in the beginning here, we can see two carbon atoms. You can see the S orbital, which is a sphere in the center, and the P orbitals, which are off to the side. On the X, Y, and Z axis. These aren't the most accurate shapes, I apologize, but it was the best I could do with this modeling. So as we come in here, if you'll notice that the S orbital combines with the P orbital to form our first bond, and this is a sigma bond. Something to note is that the first bond will always be a sigma bond between two atoms. Move the timeline along here, and we get a pi bond. So the difference between a pi and a sigma is that we can draw a line between the two red dots, the two nuclei, and pass straight through the sigma bond, but we can't with the pi bond. Let's add another pi bond. Just like that. And then let's add our hydrogens. Another sigma, another sigma. So we've got this carbon atom with two sigma bonds and two pi bonds. I'll scroll around so you can kind of see what that looks like in 3D. Wonderful. So if you are anything like me, and I was learning about hybridization and sigma and pi bonds, I looked at this carbon atom and I saw that it had two sigma bonds and two pi bonds up and down, up and across. And I was like, alright, then it has to be a hybridization of sp2. But that is incorrect. As it turns out, hybridization has nothing to do with the number of bonds an atom forms, and everything to do with the number of atoms that this carbon is connected to. This is called the steric number. A steric number is the number of atoms or groups that it's attached to, and it determines hybridization. A steric number of 2 would give you an sp hybridization. You can also just count the number of sigma bonds and that will give you the steric number. Alright, let's move to a different molecule here so we can get a little more practice. This is a carbon atom with 4 hydrogen atoms off to the side. And let's see what happens as they all come together. Once again, the s orbital comes off and we get our first sigma bond. Our second sigma bond. You'll notice a linear arrangement and the sp hybridization so far. The third sigma bond, this would be an sp2 hybridization. And finally, the last bond, which would give us an sp3 hybridization. You can also notice the shapes. We went from linear, trigonal planar, to tetrahedral, just like that. Wonderful. Just one more thing. This new molecule is ammonium. The blue is a nitrogen attached to 3 hydrogen atoms. Earlier, when we were counting the steric number, we counted the number of atoms that the central atom was bound to. But also note that a lone pair in the valence electron shell can also count towards the steric number. So this would have a steric number of 4 and a hybridization of sp3.